We are now in the process of the proof of the theorem. So the theorem is XS mu measures finite measure space one less than equal to p less than infinity, and t belongs to LP mu dash, that is it's a continuous linear functional, and then there exists unique g in LP of mu, LP dash of mu, such that t of f equals integral fg d mu over x for every f in LP mu, and norm of t is the same as norm g in LP dash. Okay, p dash is the conjugate exponent. Okay, so this is the theorem which we are trying to prove, and then in the course of the proof, so what did we do? We took, because E is a finite measure, chi E is in LP of mu, so we defined lambda E, which is equal to T of chi E, E in S, and this defined a signed measures, and lambda was absolutely continuous with respect to mu, and therefore there exists a G which is, and this also a finite measure, so G is integrable, non-negative, and such that lambda of E is equal to integral G d nu over E. And using this, so this is nothing but T of chi E is equal to integral over x chi E d mu G d mu, and then by linearity this extends to simple functions, and finally we proved that f is bounded, that is L infinity mu, then Tf is equal to integral Fg d mu over x. So this is where we stopped last time. Okay, so now we want to show that this is true in fact for all f in LP mu, not just bounded functions. Bounded functions are in LP mu because we are in a finite measure space, but otherwise we want to show this. So step 3, assume that p equals 1. Let E in S, mu E positive. Then mod integral G d mu over E is equal to integral of chi E G d mu, and that's equal to T of chi E, and that's like norm T into norm of chi E, which is mu E, norm of chi E in L1, and that is less than equal to norm T into mu E. Therefore 1 by mu E integral G d mu over E is less than equal to norm T. So this implies that G is bounded and norm G infinity is in fact less than or equal to norm T. This is by the lemma which we proved already. The average over all sets of positive measure is bounded by the same constant, then G is also bounded by that same constant. So this is okay. Then step 4. So what have we shown? If p equals 1, we have shown, so if p equals 1, that is implies G is in L infinity and norm G mu, and norm G infinity is less than or equal to norm T. That's what we have proved. Now we will show the same thing for any p. So now 1 less than p less than infinity. Okay, so psi measurable function taking values plus or minus 1 such that psi g equals mod g. So wherever g is negative, you put -1. Where g is positive, you put +1. So you get psi g equals mod g. Now you set En equal to set of all x in x such that mod gx is less than or equal to n. Okay. So this is for every n positive integer. Now you set f equals chi en mod g p dash minus 1 times psi. Define this function like this. Then f is bounded because it is outside En, it is 0. Inside En, it is mod g. G is of course less than or equal to n power something, and therefore f is a bounded function. And also mod f power p equal to chi en. Power p doesn't matter for that because it's a function which is 1 or 0. Mod g to the pp dash minus p, but pp dash, so p plus p dash equals pp dash. This is the conjugate exponent. So pp dash minus p is p dash. So that's equal to chi en mod g p dash. And fg is equal to, because psi g is equal to mod g, so you get fg is equal to chi en mod g power p dash. So we get integral en mod g power p dash d mu is equal to integral over x chi en mod g p dash, which is integral fg d mu. F is bounded, therefore this is equal to tf here. So this implies that integral mod g p dash over en d mu is less than or equal to norm t times norm f lp, but norm f lp is what? That's equal to norm t into integral over norm f. F is chi en something, so that's just integral over fn. Mod f power p is g power p dash mod g power p dash d mu whole power 1 by p. Okay, and therefore you divide this out, so you get this is norm integral en mod g power p dash power 1 minus 1 by p is less than or equal to norm t. Okay, now en increases to x, so this implies that integral over x by the monotone convergence theorem, this implies that mod g p dash 1 minus 1 by p is just 1 by p dash is less than or equal to norm t. That is, g belongs to lp dash mu and norm g p dash is less than or equal to norm t. So this is the same result which we had. G belongs to the conjugate exponent and the corresponding norm is less than or equal to norm t. So that is what we have proved up to now. Okay. So step 5. I hope I put the right step. Step 4 is, step 5. So 1 less than or equal to p less than infinity. Now, so we have shown g belong to lp dash mu and norm g in lp dash is less than or equal to norm t. Further, since mu x is finite, simple functions are dense in LP mu. Why? Because simple functions which vanish outside the set of finite measure are dense in LP mu is what we have already seen in lemma. But now, since anyway the set has finite measure, all simple functions are dense. So this implies that L infinity mu is dense in LP mu. Because L infinity mu is a bigger set than the simple functions, and therefore L infinity mu is dense mu. Further, for every f in L infinity mu, T of f equals integral fg d mu over x. Both sides agree on a dense subset of LP mu, namely L infinity mu. Both sides are continuous linear functionals on LP mu. Implies both sides agree on all of LP mu. So for every f in LP mu, you have Tf equals integral fg d mu. That is T equals Tg. But then you know that norm G ALP dash is less than or equal to norm T, but norm T equals norm Tg, which we know is less than or equal to norm G in LP dash, and therefore this implies that norm T is equal to norm G in LP dash. Okay, and that completes the proof of the theorem. So we have shown everything which we wanted to show, and therefore you have, in the case of finite measure spaces, every continuous linear functional occurs from the space of the conjugate exponent. Okay, so now let us take x s mu sigma finite. Then x is the union n equals 1 to infinity xn, mu of xn finite for all n, and xn disjoint. So you can take them all or positive measure also. Okay, so now you define h of x equals sigma n equals 1 to infinity 1 over n square 1 over mu of xn. That's all well defined because it's into chi of xn. Then sigma 1 by n square is finite, and therefore this implies h belongs to L1 of mu, and h is also strictly positive. So if you define nu of E equals integral h e d mu, then you have nu is a finite measure. Also you have that nu is absolutely continuous with respect to mu. Also h strictly positive, so this means that mu is absolutely continuous with respect to nu, because if you have nu e equal to 0, integral h over e has to be 0, but if h is strictly positive everywhere, then that must only mu e must be 0, otherwise you cannot have that thing. So you have that these two are in fact equivalent measures. Okay, so now what is integral h f phi d mu over x? This is integral over x phi h d mu, recall that. So therefore let 1 less than or equal to p less than infinity, then f belongs to LP of nu if and only if you have h power 1 by p f belongs to LP of mu. And norm f in LP nu is equal to norm of h power 1 by p f LP mu. So this gives you an isometric isomorphism between, so f going to h power 1 by p f is an isometric isomorphism between LP of nu and LP of mu. But mu is equivalent to nu, therefore L infinity mu equals L infinity of nu, and norm f infinity L infinity nu is the same as norm f L infinity of mu. There is no change because sets of measures 0 or 1 and the same. Okay. So now let T belong to LP mu prime. So define S on LP nu as S of f equals T of h power 1 by pf. This is well defined because this is in LP mu and this is for f in LP nu. So mod SF equal to T of h power 1 by p f, that is less than or equal to norm T into norm h power 1 by p f LP mu, which is equal to norm T norm f LP mu. Okay, and T of f is equal to T of h power 1 by p h power minus 1 by p f, which is less than or equal to norm S T of h power 1 by p into norm of h power minus 1 by p f in LP nu, which is equal to norm S norm f LP nu. So this implies that S is belongs to LP nu prime, and further norm of S is the same as norm of T. Because this tells you that norm T is less than or equal to norm S is less than or equal to norm T, and therefore you have, so this implies that norm S less than or equal to norm T, and this implies that norm T less than or equal to norm S. Okay, and therefore norm S is equal to norm T. So with these notations, and we now prove the following theorem. So this is called the Ris Representation Theorem. So XS mu sigma-finite measure space, 1 less than or equal to p less than infinity, T in LP mu prime, then there exists a unique G in LP dash mu, P dash equals conjugate exponent, such that T of f equals integral fg d mu over x for all f in LP mu, and norm T equals norm G P dash. So the same theorem which we proved for finite measures, we are now going to extend to sigma finite measures. So proof, so you write x equals union n equals 1 to infinity xn as above. Okay, then H, define H S as above. So nu is a finite measure and therefore SF equal to integral x fg d nu for all f in LP mu nu, and you have that norm S equals norm G LP dash nu. Now define, let's say G tilde. Okay. Now define G, which you want, as h power 1 by p dash G tilde if 1 less than equal to p strictly less than infinity, and G equals G tilde if p equals infinity, which is consistent because 1 by p dash will be 0, h power 0 is 1, and therefore we have this consistent definition. If this is sorry 1 less than p less than infinity and p equals 1. So case 1, 1 less than p less than infinity. So norm G power p dash LP dash mu. Let's compute that. That's equal to integral over x of mod Gp dash d mu, but G is what? So this is equal to integral over x h into mod G tilde p dash d mu, which is equal to integral over x mod G tilde p dash d nu because of the definition of nu, and that's equal to norm G, which is norm S p dash, okay, because S is that, and that's equal to norm T p dash. Further, integral over x, if f is in LP mu, fg d mu is equal to integral over x f G tilde h power 1 by p d mu, which is equal to integral over x f G tilde 1 minus 1 by p dash d mu, which is equal to integral over x f into h power minus 1 by p G tilde d nu, because the h d mu gives you a d nu integral, okay, h d nu, and that's equal to s of h power minus 1 by p G tilde, which is equal to f, and that's equal to T of f. So you have Tf equals integral over x fg d mu for all f in LP mu, and norm T is equal to norm G LP dash mu. So this proves the case for P. Now we only have to do the case 2, P equals 1. So this should be easier. So then you have norm G L infinity mu is the same as norm G L infinity nu, which is norm S, which is equal to norm T. And for all f in L1 of mu, you have integral over x fg d mu, which is integral over x f h power 1 by p g tilde d mu. One G is G tilde and then d mu, which is equal to integral over x f G tilde h power minus 1 d nu, which is S of h minus 1 f, which is T of f. Okay, and that completes the proof for the case P equals 1, and so we have completely proved the Ris representation theorem in the case of sigma finite measures. Now, not true if P equals infinity. That means there do exist continuous linear functionals on L infinity which do not come from an L1 function in the way we have done, because the conjugate exponent of L infinity is 1. Okay, so let us take C01 and you take which is contained in L infinity of 01. Okay, and you take T of f in C01 equals f of 0. This is well defined, and mod Tf is less than or equal to norm f infinity, and therefore this is a continuous linear functional. And therefore by Hahn-Banach theorem, T extends to L infinity 01, preserving the norm. That part is really not very important. Okay. This functional cannot be expressed as Tf equal to integral fg dm1 g in L1 of 01. This cannot be done. Assume the contrary. Assume there exists G satisfying this thing. So now you take Fn of T equals 1 minus Nt for T belonging to 0, 1 by N, and 0 for T greater than 1 by N. Okay. So this is the function Fn of T. This is 1 here. It comes to 0 at the point 1 by N and then goes on at the place 0. Okay. So then T of Fn equal to 1 for all N. But G integrable, and therefore mod Fn G. Now Fn goes to 0 pointwise, because as n goes to infinity, this function becomes more and more 0. So Fn goes to 0 pointwise, and mod fng is less than equal to mod g because fn is less than equal to 1 and integrable. Therefore, by dominated convergence theorem, you have integral fng dm1 over 0 1 goes to 0, whereas the left hand side is 1, so you cannot have, and that gives you a contradiction. So that there are continuous linear functions L infinity which do not come from L1 functions. Okay, so remark 1 less than p less than infinity, so this implies that 1 less than p dash less than infinity. So LP mu dash is L p dash mu, and LP dash mu dash equals L p mu, and it's always the same. The continuous linear function is given by the integral of a product of two functions, and therefore this implies that LP mu double dash is isometrically isomorphic to L p mu, isometric isomorphism via Ris theorem, and this implies that LP mu is reflexive. Okay, L infinity mu, L1 mu are not reflexive. L1 mu infinity equals L infinity mu, but not vice versa. So L1 mu, dash is converse is not true. Okay, now we can prove by Clarkson's inequality implies LP mu reflexive for all 1 less than p less than infinity. Okay, this Clarkson's inequality implies that LP mu is uniformly convex, which implies that LP mu is reflexive for all this. Then it is easy to prove we will see that in the exercises, this Clarkson's inequality. Okay, then it is easy to prove that LP mu dash is LP dash mu for 1 less than p less than infinity. Okay, so and this does not need mu to be sigma finite. So if you only are worried about 1 less than p less than infinity, then the Ris representation theorem is true even without the sigma finiteness property. But when you want it for 1 also, then the sigma finiteness, that's where it's really important, the rest of the proof. But the proof we have given here using measure theoretic arguments is a package deal. You get all of it together, and so 1 and p you get it all at the same time, and therefore we have presented that here. But you can purely by functional analytic methods using the notion of uniform convexity and reflexivity, we can show that for p between 1 and infinity strictly, even if mu is not sigma finite, then you have Ris representation theorem. Okay, so this completes this topic of duality. Next time we'll take up convolution.